Discussing a paper about single camera 3D reconstruction. This is a problem that is actually prevalent in autonomous driving, particularly for Tesla. It's prevalent in robotics, it's prevalent in drone technology. The problem is twofold. One is the decision to only use cameras can be deliberate, like in the case of Tesla, or it can be a problem of weight, like with drones and robots, cost and or weight. So you could be constrained by not having the ability to use either several cameras or use other sensors such as LiDAR and radar. And therefore the problem comes, what if you have a monocular camera? So you have one camera, you can take an image and you have to do a 3D reconstruction. Emphasis on 3D, which is important for robotics. Like you need to understand the depth of a chair or a piece of glass when you pick it up, a car when it passes by, let's say, a wall. It needs to understand where exactly the edges are. And monocular 3D reconstruction, according to this paper, the links in the show notes. So the problem with monocular reconstruction is accuracy, right? You have blurred edges, which can be, of course, difficult in a car setting. You want to know exactly where the edge is of a wall or another car so you don't hit it. Same with a robot. Recently, Chelsea Finn was on a podcast. She said the robotics problem is an interesting problem because the difference between grasping a glass and not grasping a glass is huge. So it's a very binary situation. It's not like in large language models where you can reconstruct a text or a Shakespeare poem and be 95% accurate and still have a good decision. Here, if you're not fully accurate and you don't grasp that thing, then you're not grasping it and you haven't done the job, and bad things can happen. So in that sense, 3D reconstruction is important. I want to talk about this paper for two reasons. One is, of course, for the technological insight and the ideas, something we do here very, very regularly at Orange Capital Partners. But also in general, I want to revisit an ARK Invest thesis that I think is interesting, which is basically the full self-drive progress is a direct function of compute. And why is that important? Well, one, that means it's a kind of a Moore's law type problem. So it's not a scientific problem or an empirical comp-sci problem anymore. It's just simply you put more compute. Now, when you put more compute into something, you actually, compute per se, of course, is useless. Like you need to have algorithms and stacks that take advantage of that compute. And this paper fits very neatly into that conversation. This is not even on podcast. It's March 26, 2025. This is Krindelko. For the day, the fund is down 4%. The market is down 2%. For the year, we're down 32%. The market is down 2%. We're down 33%. The market's down 2%. We're underperforming by 31%. So let's jump right into it. Not much to comment on the market. Unfortunately, today we have a drawdown. We had a pretty good recovery in Tesla recently. And now it's down again with the market, other than tariff battles, particularly Canada cutting ZEF credits because of internal corruption and, of course, retaliation and things like that. Nothing more to say there. It's a tough slug right now for us, I think, because we're exposed to this huge volatility and uncertainty, and also the attacks against Tesla, which is very uncomfortable. But I think this episode is a good reason for why you want to stay invested, because if full self-drive is solved, it's going to generate a lot of wealth despite all this political wrangling. So let's jump into the paper now. So 3D reconstruction for monocular camera. What's the actual problem? The problem is the following. Like when you have an image, you have to understand the three-dimensional situation. Like when you, as a human, when you walk, you have an innate understanding of depth. Like I'm walking towards a chair, I have a sense for where the chair is, I have a sense for how I can sit down. Now the reason I have a sense for these things is because we have a stereo vision. We have two eyes and the math between two eyes allows us to calculate depth, which is the early advances that Tesla did. Even back in the Carpati days, they discussed this. When they got rid of LiDAR and radar and all that stuff, they decided to solve the problem with stereo depth estimation. And that takes you quite far, but of course it doesn't take you all the way, because what if one of the cameras doesn't work? There could be glaring, there could be occlusion, there could be lots of reasons why one of the cameras doesn't work, or for that matter, one of the 8 cameras doesn't work, and then you're stuck with, you know, you could be in a scenario where only one camera is available, and you still want to be able to work with the car, or in future settings with the robot, or again, like I mentioned in the prelude, there could also be, you know, this problem could be applied to drones, where you just don't have the luxury to carry too many sensors. Maybe sometimes you only have one camera available just for weight reasons. So back to the self-driving car problem. So now, how do we measure depth? And this paper deals with the 3D reconstruction from monocular depth. As far as technique is concerned, I just want to say a few things here. So what they're doing is they're taking an input of point cloud and normals. Normals are vectors that point up from the object, and they create a field. So what they're trying to do is basically, when you have imagine you have a monocular image of a chair, and you're trying to estimate what is up and what is, you know, what is an orthogonal vector towards the surface. So a chair would show up, and a ball would show, obviously have these vectors which are, you know, kind of in a round form. You reconstruct that into a field, and then you estimate, you put a constraint on it, which is a self-attention type mechanism, where you say, okay, now given that, how do all these points relate to each other in sort of a self-attention type way? And you constrain that, so you say, well, given what I've learned in the past from objects, this type of point cloud normal that I just identified should behave like this versus like that. So you kind of try to estimate from this field, this point cloud normal field, you try to estimate the relationships and correlations between the point clouds, and reconstruct a 3-dimensional image from the 2-dimensional monocular input. So that's kind of the technology. Please refer to the paper for the details. This is not a technology podcast here, so we're not going to delve too much into the math and all that. The experiments seem successful. What we want to talk about here is more the general idea, okay? First, what we're doing here is we're trying to enhance the algorithmic approach towards a problem. And that's, I think, what's interesting here, right? Because if we want to have, if we want to work with an assumption that the problem solving in computer vision or robotics is a function of compute, then you also need to have a little bit of an idea, at least, or a strategy of how to execute you know, that compute, and how to solve problems with compute. And this is a nice example. So this problem, which again, the problem is monocular 3D reconstruction, right? So that's the problem. I can't have radar, I can't have LiDAR, I can't even have more than one camera. So how do I solve the problem? And the problem, I can solve it with more sophisticated algorithms, with more data and more compute. And let's not forget that in training, so in pre-training and test time scaling, we can actually generate data from test time scaling and use that for pre-training again. In other words, we can have images and reconstruct images and use the not so well constructed images and put them back into the training data and use them as a proxy for how to get from A to B. The nice thing about this whole thing is, of course, it's differentiable. And when it's differentiable, we can use gradient descent. And that's kind of, in a nutshell, where we think this is, you know, this is going to work. Now, before we end this, just a few things about this idea of compute being the kind of the bottleneck, but also the solution to all these big problems. Like when we have a constraint, like we have in this case. So we have a constraint. We don't have more than one camera, and we don't have other sensors. We can use algorithmic solutions and compute. We can generate synthetic data. We can use test time scaling and feed the data back into pre-training. So we can use data, generate more data, and use compute to solve the problem. And I think that's the path forward. This is the idea. This is the fundamental thesis. This is the fundamental investment thesis for Tesla. I mean, this really comes down to the investment thesis for Tesla. By the way, it also applies to maybe companies like Anduril who build, drone technology and things like that. Like, you can have low-cost solution in robotics because algorithmic solutions can bridge some of the very difficult sensor gaps. Before we end, also, I want to say one more thing, which is about vertical integration, which is, I think, very important. In the case, this paper even mentions that one of the problems that often arises, camera variability, and therefore you have to, you don't have good 3D estimation of scenes because the cameras vary. So if you're fully vertically integrated like Tesla, you can put the cameras in the camera parameters into your models, and therefore also adjust for potential accuracy issues. So to summarize, this paper is on the one hand a technical solution to a specific problem, 3D reconstruction of monocular image data, but it's also a more broader path forward in showing us how we can solve the robotics problem with compute. And I think that it's very important to keep that in mind when we work with investments like Tesla here at Launch Capital Partners, right? We have, obviously we can't predict the future, nobody can, but what you can do is you can kind of put yourself on a trajectory where technology drives you towards the goal. And you obviously have to still hope that execution happens and that there's no World War III and things like that. But at least the technology trajectory is on your side. And that's the case here. And that's why we're very optimistic about the robotics part of Tesla. Thank you.